Hi there. I'm glad you've wandered into this little pocket of quiet. Outside the busy thoughts of the day, imagine a dark sky opening soft and wide, sprinkled with the pale band of the Milky Way, like a slow path laid across the night. Somewhere along that path is our small sun, and around it, this moment we're sharing. Tonight, we're going to follow a gentle question. If you could set out on a journey from one edge of our galaxy to the other, what would that really mean? How far is far when the map is made of stars? And how long is long when time is measured in the lives of galaxies instead of days and years? We'll move through the numbers like lantern light over an old map, unhurried, warm, and easy to follow. And if this kind of quiet wandering feels like home to you, a soft like and a quiet subscribe help others find their way here too, only when it feels right. When we talk about our galaxy, we are really talking about the place that holds almost everything we have ever known. The Milky Way is not just a pale ribbon across the night, something your eyes catch on clear evenings and then forget. It is our vast address in space, hundreds of billions of stars, rivers of gas and veils of dust, planets beyond counting, and structures so wide that any attempt to describe them feels a little bit like exaggeration. Still, the question tugs at us. If you started at one edge of this great disk and tried to reach the other side, how long would that journey really be? The Milky Way is shaped a little like a glowing pinwheel seen from above, a flat disk, thicker in the middle, with long spiral arms curling outward. From side to side, that bright disk is usually said to be about 100,000 light-years across. Some careful measurements pull the number down a bit, closer to 90,000. Others stretch it upward, nearer to 120,000. That spread is already a quiet reminder of how hard this problem is. We are trying to map a forest while standing deep among its trees, with drifting fog and branches blocking our view. Dust clouds block starlight. Distances blur when they are measured in tens of thousands of light years. Astronomers spend years refining the map, using subtle clue stars that pulse in regular rhythms, clusters that move together, radio whispers from gas clouds to trace the outline of the disk. Even with all that work, there is still some uncertainty at the edges. But for our sleepy journey tonight, a round number will do. Imagine the galaxy as one grand disk, about 100,000 light-years wide, and let that be our simple measure of the road ahead. That phrase 100,000 light-years carries a lot inside it. A light-year is not a measure of time, even though the word year makes it sound that way. It is a measure of distance. If a beam of light could leave your hand and keep going, unbothered, for a full year, moving at about 300,000 kilometers every second, the path it traced would be 1 light-year long. Over all those seconds, the distance adds up to nearly 10 trillion kilometers. So when we say the Milky Way is about 100,000 light-years across, we are saying that from one side to the other, the span is on the order of 1 billion trillion kilometers. It is the kind of number that does not quite fit in the mind. Even the distance from Earth to the Sun, about 150 million kilometers, is already hard to feel. The galaxy takes that and dwarfs it again and again until the original number feels like almost nothing. Still, there are some anchors we can hold. Light itself, the fastest traveler we know, gives us a first clear answer. If you could somehow ride on a photon, a single particle of light, and send it straight from one edge of the Milky Way to the other, it would take about 100,000 years to arrive. That is the simple heart of the phrase, 100,000 light years across. 100,000 years. That is already a span 1,000 times longer than all of recorded human history. Every story ever written down, every city ever built, every war, every peace treaty, every song that has been preserved, all of it fits inside just a thin slice of that time. You could stack the entire written record of our species again and again, 1,000 times over, and only then would you reach the length of a single crossing at light speed. And yet, for us, even light speed is out of reach. According to the rules of physics, as we understand them, anything with mass can never quite touch that ultimate limit. It can get close, perhaps, but not all the way there. Our bodies, our ships, our machines are all stuck a little lower on the speed dial, so the question bends. It becomes less, how long in absolute terms, and more, how long at the speeds we might realistically reach. The fastest spacecraft humanity has ever sent into space is the Parker Solar Probe. It dives close to the sun, falling deep into the star's gravity well and whipping around at about 700,000 kilometers per hour. Compared to a car or an airplane, that speed is almost unbelievable. But set that brave little probe against the width of the galaxy and the contrast is sharp. Even at Parker's record-breaking pace, it would take well over 600 million years to go from one edge of the Milky Way to the other. Another familiar traveler is Voyager 1, launched in 1977 and now gliding into interstellar space. Voyager moves at about 61,000 kilometers per hour, much slower than Parker but still far faster than anything that stays close to Earth. At that steady pace, a full crossing of the galaxy would take more than 1.5 billion years. For comparison, Earth itself is about 4.5 billion years old. Voyager would need roughly a third of the age of our planet just to move from one side of the disk to the other, if it were even aimed that way, which it is not. Instead, Voyager is simply wandering outward, carrying with it a golden record, sounds and music, greetings in many languages, images from Earth. It is less a ship on a mission to cross the galaxy and more a quiet message in a bottle, drifting through a cosmic sea. Still, it gives us a gentle marker of our present abilities, and at the same time, it shows how small those abilities are beside the scale of our home galaxy. When we let go of real machines and step into the realm of imagined starships, the numbers can be coaxed a little closer to our wishful thinking. Suppose, just for the sake of the story, that we could someday build a vessel that travels at 1/10 the speed of light. That would be an enormous leap beyond anything we can currently construct, but it does not break the known laws of physics. At that speed, you would shorten the crossing dramatically, yet it would still take around 1 million years to get from one side of the galaxy to the other. Even a ship somehow pushed to half the speed of light would still need about 200,000 years for the journey. On paper, these numbers look like progress, but next to a human lifetime, they are still towering cliffs. For beings who live perhaps 80 or 90 years, what does it really mean to talk about a voyage lasting 200,000 years, or 1 million, or 600 million? No single person could ever set off from one edge and live to see the other. Any real attempt would belong not to individuals, but to chains of generations. You can picture a starship built for such a journey, a wandering world in its own right, where children grow up knowing only the artificial valleys and skies of the ship, where elders tell stories about a distant planet their ancestors once left behind, A destination would be an inherited idea, passed gently from voice to voice, rather than something anyone on board could expect to witness. In that kind of story, the journey itself becomes the whole point. While we imagine all this, it is easy to picture the Milky Way as a fixed background, a grand, still painting through which our little ships move. But the galaxy itself is anything but still. Over the time spans we are talking about, the Milky Way is alive with change. Stars are being born in cold, dark clouds, slowly heating and brightening. Other stars are reaching the ends of their lives, swelling into red giants or collapsing and exploding as supernovae, scattering heavier elements back into the surrounding space. Great clouds of gas and dust collapse to form new clusters. Over hundreds of millions of years, whole regions of the galaxy shift character. So when we talk about how long it would take to cross the Milky Way, we are not just talking about travel. We are talking about time deep enough that the galaxy itself would be different on the far side. The map you started with would be badly out of date by the time you arrived. Landmarks would have shifted. New stars would have kindled. Old ones would have faded. You would not only have moved through space, you would have lived through epochs. That realization adds another layer to the question: what does it mean to measure out 100,000 years, or 1,000,000, or 1,000,000,000? For us, those spans belong to geology and evolution, to the slow drifting of continents and the gradual branching of life. To link them instead to a single imagined journey, a line drawn through the galaxy, is to place ourselves gently inside a much larger story. We are not only asking how far we could go, we are noticing how vast the place already is where we quietly exist. Because, in a sense, we are already in motion. We orbit a star that orbits the galactic center, sweeping around in a huge path that takes hundreds of millions of years to complete. Our whole solar system is like a small boat tied to a much larger current, carried along whether we are aware of it or not. We will never stand outside the Milky Way and look back at it as a whole. We live inside it, always partway through the crossing. To picture where we are, imagine, again, that hazy band of the Milky Way, stretched across a dark, clear sky. To the naked eye, it looks like a cloud, a gentle stripe of pale light. Through binoculars, it resolves into countless stars packed so closely together that their light blends. That shining arch is not a local decoration. It is our edge-on view through the thickest part of the galactic disk, looking along a direction where the star density is highest. Somewhere in that glow, on one of the quieter spiral arms, our sun keeps its place. We sit about 2/3 of the way out from the center, inside a segment of arm, sometimes called the Orion Arm. From our position, the galactic center is roughly 27,000 light-years away. Even light, racing at its absolute top speed, needs 27,000 years to make the trip straight inward. When you tilt your head toward that direction on a clear night, the photons touching your eyes began their journey back, when ice sheets lay heavy over parts of Earth and human history as we know it had not yet begun. This is one more way distance and time weave together. The farther away something is in the galaxy, the further back in time we are looking when we see it. To cross the Milky Way would mean not only moving through enormous distances, but stepping through layers of history, leaving behind ancient light and entering regions whose glow might only now be brushing our telescopes. The road ahead is measured in kilometers and years, but also in the age of the light that keeps us company. To us, the Milky Way is everything. Its distances set the scale of our curiosity. Its shape and size give context to our questions. Asking how long it would take to cross it is a very human gesture, a way of trying to pull something almost incomprehensible into the circle of what we can talk about. We live our days in minutes and hours, in years and decades, so we quietly turn that same measuring stick toward the galaxy and wonder, if it were a single road, how many of those familiar units would it take to walk from one end to the other? That is why astronomers and storytellers keep reaching for analogies. Without them, the numbers just sit there like cold stones. With them, the distances become a little more touchable. You can say that if you drove at highway speed without ever stopping, you would need far longer than the age of the universe to make a full crossing. No comparison is perfect. Each one leaves something out, but together they form a gentle bridge between our everyday sense of distance and the true, enormous span of our home galaxy. Standing on that bridge for even a few quiet minutes lets us feel both our smallness and our belonging at the same time. And from that vantage, distance in our galaxy stops being just an obstacle to conquer and becomes the quiet backdrop to every dream of travel. The simple fact that light itself needs about 100,000 years to cross the Milky Way sets the scale for all our plans. It whispers what might be possible, what will likely stay out of reach, and what may live only in imagination. It also reminds us that the stars sprinkled across the sky like dust are not close neighbors in any everyday sense at all, but far-flung fires separated by gulfs so wide that our usual measures barely begin to describe them. Even the nearest suns are separated by gulfs so wide that our fastest probes would need tens of thousands of years just to visit them. The space between stars is not a narrow hallway. It is more like an ocean spread in all directions, so deep that the small wakes left by our machines barely ripple its surface. And still, the question keeps returning in the dark. How long would it take, really, to cross a place like this? Before we talk about engines and speed, it helps to sit for a moment with the size itself. A galaxy is not a single destination. It is an expanse so wide that the idea of crossing it is almost more poetry than plan. What we call the Milky Way is a vast country of stars, and we live somewhere inside it. Small, yes, but not lost. When people picture the Milky Way, they often think of that hazy band on a clear night, a pale river of light laid across the dark. To our eyes, it looks flat and cloud-like. In truth, that stripe is our edge-on view into the crowded middle of a three-dimensional structure shaped by billions of years of gravity. Stars, gas, and dust have settled into patterns. If we want to imagine any journey through it, we need at least a soft outline of that shape. Astronomers describe the Milky Way as a barred spiral galaxy. The spiral part refers to the curving arms that sweep outward from the center-long lanes, where stars and gas gather and where many new suns are born. The barred part refers to a bright, stretched-out bundle of stars that cuts across the core. From inside the disk, we cannot simply float above and take a picture of the whole thing. Instead, astronomers infer the shape from clues: how stars move, how light looks in wavelengths that slip through dust, how radio waves from hydrogen gas are arranged. Piece by piece, those clues reveal a central region that is not just a round bulge, but a bar threaded through a swollen cluster of older stars. At the very center lies the galactic bulge, a dense swarm of mostly older stars, puffed into a shape that, from the side, looks a little like a peanut. It rises above and below the thin disk. Deep inside that bulge sits a supermassive black hole called Sagittarius A*, with the mass of millions of suns quietly anchoring the inner orbits. Running through the bulge is the bar, which acts a little like a slow conveyor, guiding gas inward and helping to set the pattern of the spiral arms. From the ends of that bar, the arms unfurl, broad curving streams of stars, gas, and dust. They are not rigid rails, but regions where material is slightly more crowded than average, like a moving traffic jam. Between two of the larger arms, the Perseus arm and the Sagittarius arm, lies a smaller spur. That is where our solar system lives, in a modest branch called the Orion arm. Our whole history has played out in this quiet side lane. Most of what we see in the night sky belongs to the disk. Here live, stars of every age, glowing nebulae, star clusters, and the thin mist of gas and dust between them. Compared with its width, the disk is surprisingly slim. The main starry layer is only about 1,000 light-years thick, from top to bottom, spread across a span about 100,000 light-years wide. If you picture the galaxy as a pancake, you are not far off, though the real thing is more delicate and irregular. Above and below this disk lies the halo, a more spherical, ghostly region that holds old stars and tight globular clusters. Mixed into that halo is something we cannot see directly: dark matter. We know it is there because its gravity tugs on stars and gas, keeping them moving faster than visible matter alone would allow. The halo stretches far beyond the bright arms, wrapping the Milky Way in an invisible cocoon. Because we cannot photograph our galaxy from the outside, we lean on other galaxies and precise measurements to imagine it. Our nearest large neighbor, the Andromeda Galaxy, is another barred spiral with a bright core, winding arms, and a soft halo. Missions like Gaia, which has mapped the positions and motions of over 1 billion stars, show that our own disk is slightly warped and rippled rather than perfectly flat, a plate gently bent along its edges. All of this structure matters when we imagine a crossing. Draw a line through the Milky Way, and what you pass depends on where you aim. A route through the inner regions would thread the crowded bulge, where stars sit close together and radiation is intense. A route through the outskirts would pass more widely spaced stars and colder clouds. A path that plunges above or below the disk into the halo would move mostly through thin, ancient star fields and the faint grip of dark matter. Even the thickness you choose to cross makes a difference. The 1,000 light-years of the disk's height are still far beyond any human journey, but they are small compared with the 100,000 light-years of its width. If you include the halo, the edge of the galaxy moves outward again, perhaps to several 100,000 light-years. There is no sharp border, only a gradual fading where the Milky Way's influence gives way to intergalactic space, blending into the realm of small companion galaxies that orbit around us, and far in the future, into the slow merger with Andromeda that will reshape our home entirely. Thinking about structure also brings our own corner into focus. The Orion arm is not one of the grand main arms. It is a side road. Yet within this modest spur lies everything familiar: the sun, Earth, the planets we have visited with probes, and the constellations we trace on our sky. Nearby are places that feel almost like recurring characters. The Orion Nebula, a bright nursery where new stars are born. The Pleiades, a shimmering cluster of young blue suns. Dark clouds whose dust hides background stars like spilled ink. These are close neighbors in galactic terms, maybe a few hundred or a few thousand light years away, tiny steps on the scale of the whole disk. Even a small patch of one arm is more than full. So to cross the Milky Way would not simply mean ticking off distance. It would be like drifting through a chain of different landscapes, the crowded inner bulge, the bright star-forming arms, the calmer gaps between them, the thin, ancient halo with its globular clusters circling in the dark. Each region has its own density, its own colors, its own history written in the ages of its stars. And nothing in this picture is still. Every star orbits the galactic center, including our Sunday. We move at roughly 230 kilometers per second along our path, taking about 230 million years to complete a single loop over the age of Earth. The solar system has circled the galaxy around 20 times. When we ask how long it would take to cross our galaxy, we are laying our idea of a straight journey on top of motions that have been underway for eons. We are like passengers on an ancient train that has been looping around for ages, wondering how long it would take to walk from one end of the countryside to the other, while the landscape itself is slowly drifting. Amid all these slow orbits and shifting patterns, one traveler stands apart. Light moves through this vast arrangement with a speed nothing else can match. Before we talk about spacecraft carrying generations, or technologies that may never leave the drawing board, it helps to sit quietly with light itself, because in many ways, it has already made the crossing we are only imagining. In empty space, light travels at about 300,000 kilometers every second. In that single second, a beam of light could circle Earth more than 7 times. In a minute, it could cover about 18 million kilometers. Let it run freely for a year, and those seconds add up to nearly 10 trillion kilometers. That distance is what we call a light year. So when we say the Milky Way is about 100,000 light years wide, we mean that even this tireless traveler, racing at the universe's speed limit, needs 100,000 years to go from one edge of the galaxy to the other. To feel how remarkable that is, it helps to place it next to our own story. About 100,000 years ago, our species was still young. Homo sapiens had not yet reached every continent. There were no cities, no written words, no telescopes. Everything we think of as civilization, farming, music written down, mathematics, science, was still ahead. If a single photon had started its journey from one side of the Milky Way back then, it would only now be arriving at the far edge. All of recorded human history fits inside a thin slice of such a trip. Empires rise and fall, daily life changes again and again, and still, a beam of light crossing the galaxy would be far from done. That is the scale we touch whenever we talk about galactic crossings. We already live with the idea that light takes time, even if we rarely dwell on it. The sunlight that warms your face left the sun about 8 minutes ago. The nearest star system beyond our own, Alpha Centauri, is a little more than 4 light years away, so its light takes around 4 years to reach us. When you look at it through a telescope, you are seeing it as it was 4 years ago, not as it is in this instant. Across the galaxy, that delay stretches into hundreds or thousands of years. Some of the stars you see tonight sent their photons long before your grandparents were born. Others began their message before any human had ever looked through a telescope. Each point of starlight is, in a quiet way, a memory of how that star once was. Light does 2 jobs in this story. It is the fastest traveler and it is also the carrier of information. When astronomers map the Milky Way, they do it by collecting light in many forms: visible light, infrared, radio waves, X-rays, and more. All of these are ripples in the same electromagnetic field, all moving at the same universal speed. Our telescopes are like harbors where arriving photons are gathered and read. Instead of sending ourselves to every corner of the galaxy, we let the galaxy come to us in the form of light. Think again of Sagittarius A*, the black hole at the center of the Milky Way. It sits about 27,000 light-years away. When astronomers say they are observing it now, they are studying light and radio waves that left that region 27,000 years ago. If something dramatic happened there today, its news would not reach us for another 27,000 years. The same delay shapes any dream of conversation across the galaxy. If another civilization on the far side of the Milky Way sent us a signal tonight, that message would travel for 100,000 years before it reached Earth. If we replied at once, our answer would need another 100,000 years to cross back. A single exchange greeting and response would span 200,000 years. Communication on such scales would not be a chat. It would be more like carving words into stone and dropping them into a river that takes millennia to reach another shore. Underneath all of this sits a quiet rule from relativity. Nothing with mass can ever reach or exceed the speed of light. As you push an object closer to that speed, each extra step costs more and more energy until the required energy grows without limit. Time itself begins to behave strangely for the fast traveler. The universe seems to protect light's special status, keeping it as a ceiling no ship can touch. So when we use light as our yardstick for crossing the galaxy, we are talking about the very best case. Anything we build must move under that limit, and the time needed for a crossing will always be longer than what light requires. Even light's journey is not perfectly clean. Dust and gas can absorb or scatter it, so the messages it carries arrive a little dimmed and blurred by what they have passed through. When we talk softly about crossing the galaxy, we're really tracing paths that light has already taken. If even light needs 100,000 years, any ship made of metal and fuel would be slower. Yet there's a quiet comfort in knowing that while our bodies may never roam so far, our connection already does. Every night, photons that left their stars long before any of us were born finish their journey in our eyes. The Milky Way becomes not just a structure of stars and gas, but a lattice of light in motion, a steady rain of tiny messengers whose vast, patient flights end in one simple human act: looking up and seeing the stars. So when our thoughts turn toward speed and engines and what might come next, it helps to remember that the first traveler has already gone ahead. Light has traced the routes we only imagine, sketching the outline of our home long before any ship could follow. It quietly sets the scale, deciding what might be reachable and what will likely remain a dream. Whatever roads we picture across the galaxy, however fast we hope to go, photons will always be there first, waiting, already arrived. When we talk about crossing the Milky Way, the mind often jumps straight to distant spiral arms and far edges. But there is another way to feel the size of our home, and it starts much closer with a journey we are already on. Even now, as you listen, you are moving with the sun through the galaxy. Earth is not anchored in space. Our planet circles the sun, and the sun itself moves around the center of the Milky Way. In a very real sense, we are passengers on a voyage that began before any life stirred in Earth's oceans. We never had to build a starship to begin crossing the galaxy. We were born aboard one. Like every other star in the Milky Way, the Sun follows a path shaped by gravity. The mass of the central bulge, the dark halo, the spiral arms, and the gas between them all tug on it at once. The result is a broad, slow orbit rather than a tight little circle. At this point in its path, our star sits about 27,000 light-years from the galactic center and travels around that center at roughly 230 kilometers every second. Those speeds are invisible to us. We do not feel the motion. Night after night, familiar constellations seem to hold their places, yet, over long spans of time, the sun's movement slowly redraws the sky. Stars drift by tiny amounts against one another. Patterns stretch, tilt, and dissolve. If some patient watcher could sit on Earth for millions of years, the constellations would rearrange themselves completely. The solar system as a whole is tracing its immense orbit around the heart of the galaxy, and that orbit is not quick. At its present speed, the Sun needs roughly 230 million years to complete a single loop. One lap is longer than the entire time our species has existed. The last time our system moved through this same region of the Milky Way, Earth was in the middle of the Triassic period. There were no birds, no flowering plants, no mammals. The continents were still joined into the supercontinent Pangaea. Since the planet formed, the Sun has circled the galaxy only a few dozen times at most. Each turn takes so long that it outlasts whole geological eras. Seen from this angle, the question, how long would it take to cross the galaxy, begins to soften. We often imagine building a vessel and picking a route, but in another sense, a route has already been chosen. Our star is carrying us along a path we do not steer and cannot stop. We are walking beside the Sun, though walking is a gentle word for such speed. That path is not a neat ring on a flat sheet. As the Sun goes around, it also moves slightly up and down through the disk, weaving above and below the galactic plane. Every few tens of millions of years, the solar system drifts to one side of the midline and then crosses back. Some scientists have wondered if these slow oscillations might subtly affect Earth's history, perhaps by changing how much cosmic radiation reaches us or how often we pass near dense clouds of gas. The details are uncertain, but the larger picture is clear. Our journey is not a simple circle in 2 dimensions. It is a winding track through a 3-dimensional landscape. The Sun's orbit also reminds us that the galaxy is not an empty stage, with a few stars sprinkled on it. As our system goes around, it passes through regions of different character. Sometimes we come closer to a spiral arm, where there are more young stars, more bright nebulae, and more stellar explosions. Sometimes we drift into quieter gaps between the arms, where the star field's thin and the gas grows more diffuse. Over millions of years, these changes may gently alter the background of cosmic rays that touch our atmosphere, or the number of cool gas clouds that drift near us. We are not left bare in this environment. The Sun's magnetic field stretches outward to form the heliosphere, a vast bubble that helps shield the planets from some of the charged particles that stream through the galaxy. Inside that bubble, the planets are like cabins within a moving ship. The shape of the heliosphere shifts as we push through different regions of interstellar space. Probes like Voyager have begun to taste the edge of this bubble, giving us our first direct sense of the medium we are sailing through. Thinking about how far the Sun travels can deepen this quiet sense of motion. At 230 kilometers every second, In a single year, it moves more than 7 billion kilometers with respect to the galactic center. Over the span of an ordinary human life, the solar system sweeps through trillions of kilometers of space. None of us will live to see more than a tiny fraction of the sun's full circuit. Yet each of our lives is a short stretch of that path, like a paragraph in a book that has been writing itself for billions of years and will go on long after we are gone. From our point of view, the stars look still. From the galaxy's point of view, we are part of a restless current, carried along in a huge, slow river of stars. We are not standing at the edge, watching the Milky Way turn around us. We are inside the turning. When we ask how long it would take to cross the galaxy, it is natural to picture some future craft leaving home at great speed. But the truth is that the crossing has already begun. We are in motion, whether we notice it or not. The sun's path is also shaped by encounters. Over long times, other stars pass at varying distances. Clusters disperse, clouds of gas drift by, and clumps of dark matter exert their invisible pull. The overall orbit is not a perfect, eternal circle, but a route that slowly changes. If we could trace it through time, it would look less like a clean ring and more like a slightly wandering ribbon, nudged again and again by the company it keeps. This winding route is one reason there is no such thing as a perfectly straight line across the galaxy. Gravity curves every path. Any star that seems to head straight outward is eventually turned, slowed in one place, sped up in another, folded back into the shared dance. When we say that the sun orbits the galactic center in about 230 million years, we are really giving a gentle average, a way to describe a motion that is always being quietly adjusted. Our ride beside the sun is more than a soft image. It is part of how we learned the Milky Way is heavier than it looks. When astronomers measure how fast stars like the sun move at different distances from the center, they find that stars far out in the disk are moving faster than expected if all the mass were invisible matter. The curve of rotation stays high where simple models say it should fall. This mismatch is one of the main clues that a large amount of unseen mass dark matter extends well beyond the bright spiral arms. So when we think about crossing the galaxy, a gentle starting place is here, with the voyage that is already carrying us along. The sun is our ship. Earth is one room on board, with windows that open onto the nearby stars. Every sunrise and sunset happens inside that moving vessel. Every quiet evening spent looking up at the Milky Way is part of a chapter written while our star traces its huge, slow curve. From this intimate view, thoughts naturally return to speed in a broader sense. Whenever we imagine long journeys, our minds almost immediately come back to the same ultimate benchmark, the speed of light. Light is the fastest traveler the universe allows, the standard against which every other attempt at motion is measured. To picture riding on beams of light is to borrow, in imagination, the one pace nature never lets us reach, and to ask what the galaxy looks like when you move that quickly. At about 300,000 kilometers every second, light sweeps aside our usual sense of distance. It crosses from Earth to the Moon in a little more than a second and reaches us from the Sun in about 8 minutes. From our star to Alpha Centauri at that pace takes a little over 4 years. Stretch that same speed across the Milky Way, and the numbers become enormous again. Even racing at light's pace, a full crossing takes around 100,000 years. Relativity ties time and travel together. The closer an object with mass comes to the speed of light, the more its own time slows compared with that of those who watch it go by, and the more energy each extra step in speed demands. At the speed of light itself, the required energy grows without bound. That is why no massive traveler, no ship, no person, no grain of dust can ever quite catch up with the photons that leave a star. Light remains special, massless, and always at that ultimate limit. So, when we talk about riding beams of light, we are really talking about something that photons do, and that we join only in thought, yet the thought is still useful. It reminds us that for light, the galaxy is a kind of eternal present. Photons stream from stars, cross the dark, and arrive elsewhere without aging. For us, the same journeys stretch into deep rivers of time. Every clear night, when you look up, you are seeing the work of these travelers. The photons that touch your eye have spent years, centuries, sometimes thousands of years in flight. Each carries a small message about the place it came from, its color, its direction, the subtle imprint of the star or nebula that released it. Telescopes simply gather more of them than our eyes can manage, turning thin drizzles of light into rich images and detailed spectra. In this sense, beams of light are already our explorers. They have made the crossings we dream about, moving from star to star without engines, fuel, or rest. We ride them not with our bodies, but with our understanding. If we step back from this pure thought of light and ask what speeds we might actually achieve, the differences are stark. The Parker Solar Probe, our current record holder, moves at about 700,000 kilometers per hour, far below light speed. At that pace, a trip across the galaxy would require more than 600 million years. Even imagined craft that could reach a tenth of the speed of light would still need around 1 million years for the crossing. These numbers show how powerful light's benchmark really is. It sets a firm floor for travel time that no technology can undercut. To push even a small craft close to light speed would require enormous amounts of power. That is why some ideas for interstellar travel look to light as the thing that does the pushing, with concepts like solar sails or laser sails that let photons do the work. Even then, the Milky Way keeps its quiet scale. A probe, moving at a fifth of light speed, would still need hundreds of thousands of years to cross our home galaxy. All of this can sound distant and impossible, yet there is something gentle and grounding hidden inside these thoughts. We may never sweep from one edge of the Milky Way to the other. Our bodies may never ride on beams of light, but photons are already making those journeys for us. Night after night, they arrive from across the galaxy and fall softly onto our world. By catching them in mirrors and lenses and, sometimes, simply in our own eyes, we take part in their travels in the only way we can, by turning their long flights into understanding and into a quiet, shared sense of where we live. And every clear night when you look up, or when a telescope silently gathers a faint signal, you're watching that understanding begin. Something long and delicate is finishing its run. Beams of starlight that have been traveling for hundreds or thousands of years finally come to rest on a mirror, a sensor, or the back of a human eye. The galaxy is immense, beyond easy feeling, yet its light is always in motion, always crossing, always arriving. Inside those arrivals, we glimpse both the limits of our reach and the small, steady possibilities that still open in front of us. When we turn from those weightless photons to the machines we have actually built, the contrast is gentle but sharp. Light is the ultimate traveler, the standard the universe sets. Our spacecraft, by comparison, creep Against the backdrop of the Milky Way, they are almost still, and yet for us they are milestones, fragile proofs that we can push beyond our atmosphere and place something of ourselves into the wider dark. To ask how long it would take to cross our galaxy, we can't ignore these real ships. The story is not only about beams of light and imagined star drives. It is also about metal and wiring, fuel tanks and antennas, slowly edging outward. Their slowness is part of the answer. The fastest object we have launched so far is the Parker Solar Probe. Sent to study the Sun's outer atmosphere, it followed a careful dance of orbits and gravity assists, falling deeper into the Sun's pull and picking up speed like a stone in a well. At its peak, Parker moves at roughly 700,000 kilometers per hour, close to 200 kilometers every second. In ordinary terms, that is dazzling. At such a pace, a continent becomes a brief hop. Set that same speed against the width of the Milky Way, and it softens into almost nothing. A disk about 100,000 light-years across would take more than 600 million years to cross at Parker's best pace. The age of the dinosaurs ended around 65 million years ago. Multiply that span by nearly 10, and the journey still is not finished. Voyager 1 gives us another quiet benchmark. Launched in 1977, it wandered past Jupiter and Saturn, using their gravity to slingshot outward. It now drifts beyond the edge of the heliosphere, in the thin beginnings of interstellar space, moving at about 61,000 kilometers per hour relative to the Sunday. At Voyager's pace, a journey across the galaxy would take around 1.5 billion years, roughly a third of Earth's entire history. Laid out like this, the slow march of spacecraft is impossible to ignore. Our probes are triumphs of patience and ingenuity, but they live on scales that make galactic crossings unreachable. We send them to neighboring planets, to icy moons and distant comets, and, in the Voyager's case, just beyond the Sun's protective bubble. None is meant to cross the disk. Their lives are measured in decades, not in millions or billions of years. This does not make them less beautiful. Voyager 1 and Voyager 2 each carry a golden record, a metal disc etched with greetings in many languages, with music and sounds from Earth. They are like sealed letters cast into a vast ocean. If anyone ever finds them, they will discover not a practical tool, but a gesture, a soft statement that a small world once looked outward and cared enough to send a hello. Those bottles drift slowly. Even a single light year takes thousands of human years. That is the pace our tools achieve today. The reasons are simple and stubborn. High speed demands high energy. To push even a modest spacecraft faster and faster, you must burn fuel or harness some other source of momentum. Rockets can carry only so much propellant, and the more fuel they bring, the heavier they become, which in turn requires still more fuel to accelerate. Parker reached its record speed not by firing engines all the way in, but by falling, letting the Sun's gravity do much of the work. Voyager gained its speed from gravity assist maneuvers, borrowing a little of the giant planet's motion. These tricks let us cheat a bit, turning gravity into a kind of engine, but they have limits. Once a probe leaves the last big planet behind, its speed becomes almost fixed. From that point on, it glides tireless, but slow on the scale of the galaxy. There is also the question of endurance. Suppose we somehow manage to accelerate a craft to a much higher speed, perhaps a noticeable fraction of the speed of light. It would then face a journey lasting hundreds of thousands or millions of years. Electronics decay, Materials fatigue, power sources run down. A grain of dust that would be harmless at ordinary speeds becomes a tiny bullet at near-light ones, capable of shredding a hull or frying delicate instruments. Interstellar space is thin, but over vast distances, even rare encounters add up. Our current spacecraft are not built for that. They are made for decades, not eons. Still, the slow march tells us something important about the space between aspiration and reality. On paper, we can talk about photons crossing the galaxy in 100,000 years. In our minds, we can place starships at fractions of light speed and watch the numbers shrink. But when we stand beside real launch pads and count down to actual flights, the timescales change. The gap between a photon's journey and a probe's journey is the gap between what the universe allows in principle and what our hands can currently build. It would be easy to feel small in the face of that gap, yet over the short span in which we have been sending machines outward, the trend is encouraging. Each generation of spacecraft tends to reach a little farther or move a little faster. Parker is swifter than Voyager, which was faster than the missions that came before it. Ideas for nuclear propulsion, fusion drives, and light sails are already being studied. Measured against the galaxy, the increase is tiny. Measured against our own story, it is meaningful. It also changes how we feel about time. Human history and writing stretches back only a few thousand years. The life of a spacecraft is shorter still. Place those spans beside the hundreds of millions or billions of years needed for a galactic crossing at current speeds, and they collapse into thin lines. No probe we build today will ever cross a noticeable slice of the Milky Way, but these early machines are still the first small footprints on a shore, evidence that we have begun to move at all. Whenever we rest with these thoughts, another layer of the story comes into focus, the hard boundary that no amount of cleverness can erase. We can imagine better engines, lighter materials, more efficient ways to gather and store energy, but above all of it hangs one unmovable rule: the speed of light. Physics does not treat this as a puzzle to be solved. It treats it as a condition, a built-in feature of reality. Nothing with mass can move faster than light through empty space. This is not a technical snag waiting for a breakthrough. It is a ceiling woven into the way space and time themselves behave. The number is straightforward enough: about 300,000 kilometers each second. A beam of light can circle our planet 7 times in the span of a heartbeat. In a year, it covers nearly 10 trillion kilometers. Stack up 100,000 of those yearly distances, and you have a rough measure of our galaxy's width. The deeper difficulty lies not in the size of the number, but in the impossibility of stepping beyond it. As something with mass accelerates, each extra notch of speed costs more energy than the one before. At everyday velocities, this effect is invisible, but as you approach higher fractions of light speed, the curve steepens. To actually reach light speed would require infinite energy. The universe, in other words, bars the door. We can lean close to it, but we cannot go through. This is not just elegant mathematics. In particle accelerators, tiny charged particles are whipped around rings at speeds so close to light that the difference hides in the decimals. No matter how much energy scientists pour into them, those particles never reach the full speed of light. Only massless particles, photons, and a few cousins are allowed to live exactly at that boundary. For crossing the galaxy, this rule has deep consequences. Even if we learn to build engines that push ships to astonishing velocities, we will never quite match the pace of the light that paints our night sky. The absolute best case is set, 100,000 years for a massless traveler to cross from one side of the Milky Way to the other. Any real ship, dragging its mass and its passengers along, must take longer. Relativity also folds time into the picture in a strange way. As an object moves faster, time for that object slows compared with the flow of time seen by someone who stays behind. A hypothetical starship cruising at a high fraction of light speed might find that, on board, only a few decades pass during a journey that looks, from Earth, like centuries. In principle, a crew could leave Earth, accelerate to such speeds, and reach distant regions of the galaxy within a single lifetime, measured on their own clocks. But when they arrived, hundreds of thousands of years might have passed back home. Civilizations would have come and gone. Languages, cultures, even species could have changed. Time dilation does not break the speed limit. It only reshapes how journeys are felt. For the question of crossing the Milky Way, it means we must hold two truths at once. From the outside, a crossing always takes at least 100,000 years at light speed, and far longer, more slowly. From the point of view of a near light speed traveler, the experience time could be much shorter. The universe allows that kind of personal shortcut, but it never allows information, matter, or ships to outrun light. The same limit governs how we speak, not just how we move. Radio waves, laser pulses, any signal we can send, all obey the speed of light. If a civilization on the far side of the galaxy sent us a greeting tonight, we would not receive it for 100,000 years. If we answered it once, our reply would take another 100,000 years to return. One exchange, one question, and one answer would span 200,000 years. Physics does not forbid such communication. It only insists that it be slow. On Earth, speed limits are often things we dream of, outgrowing with better machines. A faster car, a stronger aircraft, a more efficient rocket can always be imagined. The speed of light is different. No clever engineering can erase it. It is not a hurdle in our path, but the shape of the path itself. Ideas about beating the limit sometimes turn to more exotic notions that bend space itself instead of pushing through it. For now, they live mostly on paper and in stories, ways of exploring the edges of what might be allowed, not plans we can mark on a calendar. So the speed limit of light stands where it has always stood, firm, unshaken. It can feel, at first, like a fence drawn a little too close around our hopes. But it also does something quieter and more reassuring. If signals could move faster than light, the order of events could twist. Causes might follow effects. Consequences could ripple backward. By keeping light as the upper bound, the universe keeps its own story in order. Time flows in one direction. Events line up in a way that can be understood. For our gentle question about crossing the galaxy, this means we must fold humility into our wonder. The Milky Way is wide enough that even the fastest possible messenger needs 100,000 years to span it. Every spacecraft we design, every propulsion method we dream about, must live within that frame. The speed of light is not a suggestion. It is the canvas on which all our journeys are drawn. And within that canvas, there is still room to imagine and to learn. Time dilation leaves open futures where travelers see more of the galaxy than those who stay home, even if they return to a world changed almost beyond recognition. Slow messages exchanged across thousands of years are still messages. Ships that reach only the nearest stars are still bridges. The limit is absolute, but it does not empty the story. Instead, it gives its shape a set of quiet rules. within which we can keep wondering how far we might go and how long it would take to wander from one side of our spiral home to the other. Every question we ask about travel in the Milky Way leans on the same quiet reference point. Whether we're dreaming about riding beams of light, sending radio messages, or pushing metal ships into the dark, everything is measured against one simple limit: the pace at which light moves. That limit will not bend for us, but it does something generous. It gives our questions edges. Because light has a fixed speed, the galaxy is not just a blur. It becomes something we can measure, even if we may never touch every place we measure. So when we whisper about crossing our galaxy, the first thing we need to understand is not speed, but size. How wide is our home? How deep is the distance we are imagining? It sounds simple to say that the Milky Way is about 100,000 light-years across, but that smooth number hides centuries of trial, error, and patient refinement. Measuring a galaxy from the inside is one of astronomy's hardest problems. We cannot float outside the spiral and take a portrait. Everything we know has been stitched together from within, like mapping a forest while standing among the trunks, with fog and branches blocking most of the view. Long before anyone spoke of light years, people simply saw the pale band across the sky and wrapped it in story. Some called it spilled milk from a goddess's hand, others a silver river or a road of souls. None of those tales counted kilometers, but they all carried the same feeling. Whatever that stripe was, it was not small. Human eyes have been catching it for as long as we've had nights. The first careful attempts to turn that feeling into numbers came much later. In the 18th century, William Herschel and his sister Caroline swept the sky and counted stars, reasoning that directions with more stars must mark thicker parts of the Milky Way. From those counts, Herschel sketched a flattened disk and placed the sun near its center. He had the disk right, but dust played tricks on him, hiding stars in some directions and making the sun's neighborhood look more central than it is. In the early 20th century, a quiet revolution began with small, regularly pulsing stars called Cepheid variables. Henrietta Leavitt discovered that the brighter a Cepheid truly is, the slower it pulses. That simple link turned certain stars into distance markers. Using these beacons, Harlow Shapley mapped ancient star clusters and realized that they formed a great swarm centered not on the sun, but far away towards Sagittarius. From this, he inferred that the Milky Way was tens of thousands of light years across, and that the sun sat off to the side in one of its arms. New tools brought new clarity. Radio astronomy let us listen through the dust that blocks visible light. Neutral hydrogen gas emits radio waves at a wavelength of 21 centimeters, and by mapping that glow across the sky, astronomers trace the lanes of gas that outline the Milky Way's spiral arms. Infrared telescopes added more detail, peering through dusty regions to reveal stars crowded along the galactic plane. Piece by piece, the hazy band became a barred spiral with a central bulge, a narrow bar, and arms winding outward. In recent years, the Gaia spacecraft has refined this sketch with remarkable precision. Since 2013, it has been measuring the positions and motions of more than 1 billion stars, not as flat points, but as locations in three-dimensional space. Out of those measurements comes a living map, a disk about 100,000 light-years wide, slightly warped and twisted, wrapped in a larger, more diffuse halo that may reach 2 or 3 times farther. Gaia has revealed ripples in the disk, streams of stars left behind when smaller galaxies merged with ours, and other subtle signatures of the Milky Way's long history. Measuring the galaxy is not only about span, but also about weight. By watching how fast stars orbit at different distances from the center, astronomers draw what is called a rotation curve, a graph of speed versus distance. If only the visible stars and gas were present, the outer regions should orbit more slowly, the way far-out planets move more gently around the Sunday. Instead, the speeds stay high. It is as if the whole galaxy were being held together by an extra, invisible mass. We call this dark matter, something that does not shine or absorb light, but whose gravity is undeniable. It seems to wrap the Milky Way in a vast, unseen halo, providing most of its mass and keeping the fast-moving outer stars from drifting away. So when we quietly say about 100,000 light-years across, we are standing on the shoulders of all this hidden work: star counts, variable stars, radio maps, space telescopes charting motions too small for us to feel. Each method has its limits. Each sees only part of the whole. Together they sketch a consistent picture: a bright disk, a barred center, spiral arms, a warped shape, an extended halo. The sun sits about 27,000 light-years from the center, tucked into a modest spur between larger arms, one ordinary star among hundreds of billions. Details are still being argued over: exactly how far the halo stretches, how many main arms there are, how much dark matter surrounds us. None of those questions has a perfectly sharp answer yet. The Milky Way is not a tidy object with crisp edges. Its outskirts fade into intergalactic space. Its arms split and merge. Its shape ripples and shifts as time goes on. Measuring such a thing is less like drawing a perfect circle and more like tracing the outline of a drifting cloud. For our purposes, though, the rounded numbers are enough. To say 100,000 light-years is to set the size of the stage. It tells us that even light, racing at the universe's top speed, needs that long to cross the disk. Any spacecraft, no matter how advanced, must take longer. That single measurement gives shape to every later question and gently fixes our address, neither at the center nor at the edge, but partway out in a quiet lane, circling with countless other stars. Thinking about how hard-won these measurements are can change the way we see that faint band above us. From the ground, it could be mistaken for a simple glow. Only through centuries of watching, recording, and refining did it resolve into a vast spiral with a bar and bulge, arms and halo, dark matter, and a central black hole. Measurement turned a blur into a structured home, with rooms we can name, even if we can never walk them. And yet, even with all this structure in mind, the Milky Way remains too large to hold as a single feeling. So we often turn back to the traveler that made those numbers possible: light itself. If there were a way to do what light already does, to move at 300,000 kilometers each second, the galaxy would change from an almost unreachable distance into a path that, while still enormous, has a clear, definite length. We cannot truly ride on a photon. Photons have no mass and do not experience time. They are not seats we can slip into. But there is value in following one in imagination, just long enough to feel the scale differently. Picture that you could cling to a single photon leaving our Sunday. In about 8 minutes, you reach Earth's orbit. The distant sunlight crosses every day to warm our seas and skies. A few hours more carry you through the orbits of the outer planets, By the end of your first day, you have already swept past the distance of Voyager 1, the farthest spacecraft we have ever launched. What took us decades of effort, light covers in less than 24 hours. You keep going. In a little over 4 years, you rush past Alpha Centauri, the nearest other star system. After roughly 9 years, you leave Sirius behind, the bright star that anchors our winter evenings. Within a few decades, the familiar constellations have fallen away into new patterns. The Orion Nebula, a glowing cradle of young stars that feels so far even through a telescope, lies behind you after a little more than 1,000 years. From our human vantage point, 4 years or 1,000 years are vast stretches longer than most plans, longer than any memory. Yet compared with the road still ahead, they are only the first steps. Your photon is not heading for a nearby star, but traveling across the whole disk, even at light speed. That crossing takes about 100,000 years. A photon that left one edge when humans were first painting in caves would still be mid-journey today, its arrival waiting tens of thousands of years in the future. This is the cleanest, most generous case the universe allows. A massless traveler, moving at the absolute speed limit, needing 100 millennia to cross our home. Everything slower stretches the journey even more. Our present-day spacecraft would need hundreds of millions or billions of years. Even speculative ships moving at a significant fraction of light speed would count their trip in hundreds of thousands of years. The photon's journey is the lower bound, the best we can possibly do in principle. And yet, photons make journeys like this constantly. Every star pours out light in all directions. Some photons leave the Milky Way entirely, racing into the deep dark between galaxies. Others glide from one arm of the disk to another. A tiny fraction happen to arrive here, meeting rock, cloud, metal, water, and skin. Each carries a trace of where it has been, a color, an energy, a direction. To hitchhike on a photon in the real world is to receive it, to let it strike a detector or an eye and turn its long, silent flight into a small piece of understanding. Astronomers have been doing this patiently for a long time. When they image a star cluster, they are catching photons that left those stars hundreds or thousands of years ago. When they study the glow near the galactic center, they are seeing light that began its trip around the time humans first told stories under open skies. Every observation is a kind of gentle hitchhiking, riding backward along a photon's path in thought, all the way to its origin. If you could truly ride with one, your sense of distance would collapse. The gaps between spiral arms that we describe in tens of thousands of light years would pass without any felt delay. Whole regions of the galaxy would flicker past. For light, there is no too far, only not yet arrived. For us, bound to slower speeds and brief lives, that contrast can feel overwhelming, but also clarifying. It shows us the best-case journey, the clean edge of what the universe permits, and helps us feel just a little more clearly what it means to talk about crossing our galaxy at all. To picture yourself hitchhiking on a single photon is to lean for a moment into the stream of the cosmos and watch an impossible distance fold into something almost simple. When you step back from that imagined ride and return to the slower rhythm of metal and fuel, the contrast can feel humbling but also strangely comforting. We may never ride with photons in the literal sense, yet we live inside their journeys. They wash over our planet from every direction, carrying news from nearby stars and distant nebulae, from the crowded center of the galaxy and the quiet outskirts. Through them, we know where we are. They are our messengers, our explorers, our silent traveling companions, whether we notice them or not. With those flickers of light as guides, we can turn towards something closer to our own pace, the small machines we have actually sent outward. When people think of our first real steps into the wider galaxy, two names almost always drift up first, soft and familiar: Voyager 1 and Voyager 2. They are not fast compared with light. They were never meant to cross the Milky Way, yet they hold a special place in our imagination because they are the first of our creations to slip beyond the sun's protective bubble and feel interstellar space directly. Voyager 1 left Earth in 1977, followed by Voyager 2 on a slightly different path. Their first assignment was to visit the outer giants of our solar system. Voyager 1 swept past Jupiter and Saturn, sending home views of storms, rings, and moons in detail no eye had held before. Voyager 2 took the longer route, visiting Jupiter, Saturn, Uranus, and Neptune in turn. With those flybys, the twin spacecraft became the only messengers we have ever sent to all four outer giants, turning distant points of light into worlds with weather and history. When the planetary tour ended, the Voyagers did not. Their paths simply carried them outward. Year after year, they drifted farther from the sun, their instruments still listening. At last, they crossed the edge of the heliosphere, the great bubble carved by the solar wind, and slipped into the thin sea between the stars. Voyager 1 now floats tens of billions of kilometers from home. Voyager 2 follows on another line. For the first time, human-made objects are moving through true interstellar space. For something built in clean rooms and launched from one small world, that is extraordinary. And yet, laid against the width of the galaxy, the Voyagers are barely moving. Voyager 1 travels at about 61,000 kilometers per hour, roughly 17 kilometers every second. At that pace, a single light year would take more than 17,000 years to cross. Alpha Centauri, the nearest star system, lies a little over 4 light years away. Even that short hop would take around 70,000 years. To drift from one edge of the Milky Way to the other at Voyager's speed would require roughly 1.5 billion years. From the galaxy's point of view, their progress is almost nothing. They will never come close to another star in any time span that means anything to us. Their power supplies will fade, and their instruments will fall silent long before they have crossed even a tiny fraction of the disk. But from our point of view, their journey is immense. They are the farthest outposts we have. Every whisper of radio they send back travels for more than 20 hours at the speed of light and still arrives clear enough to be read. Each of those whispers comes from a small, aging craft with a dish patiently pointed at a pale speck in the dark. Their instruments taste the interstellar medium and report the density of plasma, the strength of magnetic fields, the flux of cosmic rays. Before them, these were quantities we could only infer. With them, we are touching that environment, just a little, from within. And then there are the golden records. Bolted to each Voyager is a metal disc, copper-plated with gold engraved with a tiny archive of Earth, greetings in many languages, music from different cultures, images encoded as patterns, and simple sounds: the wash of waves, the rustle of leaves, a heartbeat, a baby's first cry. Diagrams show how to play the record and how to find our sun using the regular ticking of distant pulsars. No one seriously expects that another civilization will ever find them. The odds are tiny. The records are not a practical message so much as a gesture, a quiet note that says, "We were here, we looked outward, we cared enough to leave something of ourselves behind." On the scale of the Milky Way, the Voyagers are grains of dust. Their mass is negligible. Their paths through space are almost invisible, but for us, they are landmarks. They prove that a young species can, with enough patience, place fragile instruments beyond the reach of its own star's wind and still hear their voices decades later. They show that distance, while daunting, is not absolute. There is a difference between never and not yet. It is oddly soothing to think about what will happen to them after the last signal fades, long after their power has drained away and their transmitters have gone quiet. The Voyagers will go on coasting through the galaxy. In the deep cold between the stars, their golden records may last for hundreds of millions of years, scratched only by the rarest dust. Long after cities have crumbled and languages on Earth have shifted beyond recognition, those little craft will still be drifting, carrying a fossil of our moment in time. Seen from that long vantage, they are like the first seeds tossed into a vast, dark field. Most seeds will never find soil, but the act of scattering them matters. The Voyagers remind us that exploration is not always about arriving somewhere. Sometimes it is about sending something fragile and hopeful into the unknown and allowing time to decide what comes of it. Placed beside a photon's effortless dash, their progress looks painfully slow. A beam of light crosses the distance from the Sun to Voyager, 1 inch a few hours. Voyager itself would need tens of thousands of years to bring its small body that far under its own power. The ratio between light and metal is the gap between what physics allows in principle and what we can build in practice. The Voyagers drift inside that gap, tracing its outline for us. Their story also nudges us toward a different kind of journey, one that does not belong to any single crew. When we look at the times required even for the nearest stars, it becomes clear that no person could ever set out, travel, arrive, and return within one lifetime. Our bodies are too fragile, our years too few, so the idea of travel stretches. Instead of thinking in terms of individuals, we begin to think in terms of chains of people linked across time. This is where the notion of a generation ship appears, not as a blueprint, but as a gentle thought experiment for journeys longer than a human life. A generation ship is built on a simple idea with deep consequences. If a voyage will take centuries or millennia, then the crew must be a continuing community. Children are born on board, grow up, grow old, and die inside the same vessel. Their children, and then their children again, carry on. The ones who finally arrive are the distant descendants of those who left. Even at 1/10 of light speed, a velocity far beyond anything we can currently reach, a star 100 light-years away would demand roughly 1,000 years of travel. To cross the full width of the Milky Way at that pace would take about 1,000,000 years. These numbers are not measured in birthdays but in eras. The people who step onto such a ship would know from the beginning that the goal is something they can help aim toward but will never personally see. Life on such a vessel would be a world in itself. Instead of oceans and mountains, there would be decks and greenhouses under artificial suns. Instead of changing seasons, there would be the steady hum of life support systems and the slow, almost unnoticeable drift of stars outside. For those born aboard, the idea of a distant planet at the end of the journey might feel abstract, almost like a legend. Their real home would be the ship's corridors, its air, its stories. The questions that follow have little to do with hardware and everything to do with meaning. How do you keep a purpose alive for 10 or 20 generations? The first crew might be carried by the thrill of departure. Their grandchildren might know the mission mostly from lessons and stories. Centuries later, the original destination could feel remote, while daily life centers on harvests in hydroponic gardens, repairs to the hull, friendships, and disagreements in a sealed community. The voyage might sink into the background as a shared myth, or it might become the core of identity, not citizens of the world left behind or the world ahead, but citizens of the journey itself. Because of these complications, some people imagine other options: tiny probes that can repair themselves, ships that carry frozen embryos, or seeds and instructions rather than living adults, swarms of robots instead of one fragile community. Machines do not feel boredom or grief. They can, in principle, wait for 1,000 years or 10,000 without complaint. But even if such approaches become practical, the idea of a human generation ship still pulls at us. It is less about efficiency and more about continuity, about seeing ourselves as threads in a tapestry that stretches beyond a single life. In that way, the galaxy asks something of us that goes beyond engineering. It nudges us to think in longer arcs, to imagine commitments that outlive their starting point, to find meaning in being part of a story we will not see completed. Light can cross the Milky Way in around 100,000 years. Our current probes would need hundreds of millions or billions. Somewhere between those extremes lies the possibility of journeys measured in lifetimes stacked upon lifetimes. We do not know whether we will ever build such ships or choose instead to send only our machines and our messages. But by tracing these possibilities, we begin to feel the true scale of our home and the depth of patience it demands. The Milky Way will not hurry for us. It turns at its own slow pace, arms winding and unwinding over aeons, while light and dust and small, hopeful objects like voyagers drift along its curves. To ask how long it would take to cross it is, in the end, to ask how far we are willing to let our imagination and our sense of responsibility extend past one lifetime, past one century, and out into the long, quiet future where our descendants, or our machines, or simply our traces might continue the journey we have only just begun. There's a quiet honesty in admitting that a task is too large for a single life. The only way beings like us could ever truly approach a journey across the Milky Way is by stretching our sense of we and when far beyond one lifetime. A crossing like that would never belong to one person or even one era. It would belong to whole chains of people, to cultures that hand the idea forward like a lantern. Generations would be the true currency of such a voyage. When the scale of the galaxy starts to feel overwhelming, the mind naturally reaches for a loophole. If even light needs 100,000 years to traverse the disk, maybe there is some other path we've missed. That is where thoughts of warp drives and wormholes drift in soft, half hopeful, half curious. They are not blueprints we can follow today, and they may never become real hardware, but they show how far imagination tries to lean when distances begin to feel impossible. Both ideas come from the same deep place in physics, Einstein's picture of space and time as a flexible fabric. General relativity says that mass and energy curve space-time, and curved space-time tells matter how to move. The equations that describe this are subtle, but when you play with them, you discover strange shapes hidden inside. One of those shapes is the warp bubble, imagined by physicist Miguel Alcubierre in the 1990 seconds. In his setup, you do not try to push a ship through space faster than light. Instead, you ask, what would happen if space itself could be made to flow? The mathematics allows a kind of wave, space-time, squeezed in front of a bubble and stretched behind it. The ship sits inside, locally at rest, like a passenger in a calm pool, while the riverbed slides beneath. To faraway observers, the bubble could move faster than light without the ship ever breaking the local speed limit, because it is not the ship outrunning light, it is the stage itself being rearranged. On paper, this works. In reality, the hurdles loom like mountains. Creating such a bubble seems to require a form of negative energy, something that pulls instead of pushes, bends space-time the other way. Tiny hints of effects that look like this exist in quantum theory, but only in vanishingly small amounts. The energy needed for a macroscopic warp bubble, even in optimistic refinements, is still beyond anything our sun produces in its lifetime. Elegant equations do not automatically become engineering. Wormholes offer a different dream. Rather than riding a wave of moving space, you imagine punching a tunnel through space-time itself, linking two distant points with a short, hidden corridor. Step through one mouth, emerge from the other, and you have taken a shortcut that ignores the long arc between. The idea grew from early solutions to Einstein's equations, the so-called Einstein-Rosen bridges, and was later explored by John Wheeler and others. As with warp bubbles, the traveler never exceeds the speed of light locally. The trick is that space-time has been folded, so the long road is now a single step inside the tunnel. Again, the problems are severe. Wormholes, as the equations describe them, want to pinch closed. To keep them open long enough for anything to pass through, you once more need exotic negative energy. Without it, the throat collapses faster than light could cross. We do not know how to create such a structure, or even whether large, stable wormholes can exist in nature at all. Some theories of quantum gravity hint at microscopic tunnels flickering in and out of existence at scales far smaller than atoms, but none have been seen, and none are big enough to carry even a dust grain. Still, these ideas linger at the edge of our thoughts for a reason. They remind us that space-time is not a rigid backdrop. The same equations that give us black holes also allow, at least on paper, for warp bubbles and wormholes. They live in a strange category, not obviously forbidden, not remotely practical. Sitting in the space between impossible and unknown, they also carry their own complications. Certain warp and wormhole setups seem to allow loops in time-closed paths where you could, in effect, arrive before you left. Stephen Hawking once joked about a chronology protection built into the universe, a way for physics to quietly forbid time machines before they create paradoxes. Many physicists suspect that some deeper rule will prune these exotic solutions away or make them self-destruct whenever they threaten to tangle cause and effect. Whether that is true or not, these speculative shortcuts serve a purpose. Faced with a galaxy so wide that even light takes 100,000 years to cross it, they give us a language for wondering, what if space itself could help? They let us frame the problem clearly. Faster than light motion through normal space is truly impossible. reshaping space so that distances change might, just barely, be something nature allows. We do not know, but the simple fact that the equations leave room for the question pushes us to study them more deeply. It nudges science forward, and on quieter nights, it gives the imagination something to play with. After wandering through those far edges of theory, it can feel steadying to come back to a different kind of loophole, one that does not break any rules, but bends our expectations. Relativity does more than set a speed limit. It also tells us that time itself is not the same for everyone. How long a journey takes depends on whose clock you trust. In our everyday lives, time feels universal. A minute for you is a minute for me. A year passes, and everyone's calendars turn together. Einstein's special relativity, published in 1905, gently breaks that assumption. It says the speed of light is fixed for all observers, no matter how they move. To preserve that constancy, space and time must stretch and squeeze. Lengths contract along the direction of motion. Clocks tick at different rates depending on their speed. None of this is noticeable when you drive a car or fly in a plane, but at velocities close to light speed, the effects become profound. This slowing of time for fast travelers, time dilation, has been tested again and again. Identical atomic clocks flown on airplanes or orbiting in satellites return ever so slightly behind their twins left on the ground. Particles created in accelerators, which should decay in a fraction of a microsecond, live many times longer when moving near light speed. Their internal heartbeat slows from our point of view, exactly as the equations predict. Now imagine applying that to a journey across the Milky Way. From Earth's perspective, the arithmetic is simple. Even at 90% of light speed, a straight crossing still takes a little over 100,000 years. No ship launched from our century could arrive before any trace of our current languages and cultures had faded. But for the crew on board, the story could unfold differently. The closer their speed comes to light, the more their own time stretches out compared with Earth's. At 90% of light speed, the dilation is modest but real. Tens of thousands of years might pass on Earth, while the travelers experience less. At 99.9%, the effect grows dramatic. A journey that looks, from the outside, like 100,000 years could be squeezed into a span closer to centuries or even decades for those inside the ship, depending on how they accelerate and decelerate. To them, daily life would feel ordinary. They would wake, work, rest, watch the stars drift slowly past. Meanwhile, back home, whole ages would turn. This is the heart of what people call the twin paradox. One twin stays on Earth, while the other departs on a near light speed voyage. When the traveling twin returns, they are younger. Their body and their clock have ticked through fewer years than their siblings. The paradox is only apparent when you include the full story, the accelerations, the changes of frame it resolves cleanly. Experiments with fast-moving particles mirror the same effect, but the emotional weight remains. Two people who began together no longer share the same slice of history. Extend this idea from stars nearby to the full breadth of the galaxy. In principle, a ship could be built to accelerate to speeds so high that, on board, the crew's subjective time for a crossing of the Milky Way is less than a lifetime. They might set out as young adults and arrive gray-haired but living at some distant spiral arm. From their perspective, the crossing only took decades. From the galaxy's perspective, and from any clock left near Earth, roughly 100,000 years or more have passed. That split answer sits at the center of the time dilation puzzle. Ask, how long does it take to cross the Milky Way? And relativity quietly replies, it depends who is asking. One answer belongs to the outside world, counting every year that passes as the ship glides along its path. The other belongs to the travelers, whose own time has been stretched and slowed by their motion. Both answers are true. They simply live in different frames. This has deep consequences for what such journeys would mean. Time dilation offers a kind of personal loophole for the crew. They can, in principle, see more of the galaxy than their lifespan would normally allow. But the price of that shortcut is separation. When they arrive, the world they left will be gone, transformed by 100 millennia tides of geology, biology, and culture. Even if descendants of humanity still exist, they will be strangers, speaking languages the original crew never heard, living under skies reshaped by continental drift and shifting constellations. Communication during the journey would also become more and more abstract. Messages sent back and forth would take thousands of years each way. Conversations would stretch beyond meaning. Experiments on Earth hint at this reality in miniature. Muons, fleeting particles created when cosmic rays hit the atmosphere, should decay almost instantly. Yet many reach the ground because, in their own fast-moving frame, less time has passed. Their little lives are extended by their speed. On starships, the same principle would hold for human cells and human hearts. The travelers would not feel their time slowing. Their clocks and bodies would seem perfectly normal to them. Only when they compared themselves to the slow ticking of distant Earth would the difference show. In this light, time dilation becomes both an invitation and a warning. It says, yes, you can, in theory, reach distant parts of the galaxy within a human life, and at the same time, you will not return to the same universe you left. It suggests a Milky Way that could eventually be dotted with far-flung human or post-human communities, each one launched by a small group who chose to step into a different river of time. Those communities would be separated not only by distance, but by history they did not share, unable to talk to one another in any immediate way. The galaxy could be crossed, but not tied tightly together. In the end, this is what the time dilation puzzle gives us. Not a neat solution, but a deeper sense of what we are really asking when we talk about crossing the Milky Way. We are not only asking, how fast can we go? We are also asking, whose clock do we trust, and what are we willing to leave behind? Relativity doesn't remove the distance, but it shows that distance and time are woven together. Any path we take across the galaxy will tug on both, and any answer to how long will always carry, quietly behind it, the question, for whom? If you picture the Milky Way as a road, it can feel like an impossible one, too long, too dark, too full of strange turns. But by now the shape of that road is a little clearer. We've met the limits of speed, watched light make the crossing in imagination, followed the slow progress of our probes, and felt how time itself behaves differently for travelers and for those who stay home. We've brushed past black holes, reading them as both warning signs and ancient mile markers, and we've seen how the stars themselves draw a map in their light. With all of that in mind, the simple question that started this wandering, how long would it take to cross our galaxy, begins to soften. There is an answer in numbers, yes, but there is also an answer in feeling, The numbers tell us about years and speeds. The feeling tells us about what it means to live inside something so large that even light must hurry for 100,000 years. On the strictest terms of physics, the outline is straightforward. If you were a photon leaving one edge of the Milky Way and heading straight across, you would arrive at the far side about 100,000 years later. No matter how clever our engines become, no ship made of matter will do better than that. At the speeds our current spacecraft achieve, the same journey stretches into hundreds of millions or billions of years longer than many species last, longer than most worlds stay unchanged. Even if we imagine miraculous drives that can push a ship to a hefty fraction of light speed, the crossing still takes hundreds of thousands of years, as seen from the outside. Relativity opens a small window in that wall. For travelers willing to accelerate close enough to the speed of light, time on board could be compressed. Their own clocks might count only decades, while the galaxy's clocks count millennia. From their perspective, the Milky Way would seem to contract along their direction of travel, its breath squeezed into something a single lifetime can hold. From our perspective, watching from some quiet arm where we began, their journey would sweep across ages. Both views are true. The crossing could, in this tilted sense, be made within a human life, but only by letting go of any hope of staying in step with the world left behind. Generation ships offer a different path to the same dream. Instead of leaning on relativity, they lean on continuity. A vessel that travels more slowly but supports a self-sustaining society could in principle drift between stars over centuries or millennia, each generation living its own complete life inside the long arc of the voyage. In that picture, the crossing is not something a single person survives, but something a culture inhabits. The Milky Way becomes less a distance to conquer and more a habitat to grow into arm by arm, system by system, step by slow step. Around all of this, imagination has tried to carve shortcuts, bending space with warp bubbles, stitching distant points together with wormholes. On paper, some of these paths are not forbidden. The equations of gravity do not slam every door, but the prices they ask exotic matter, impossible energies, troubles with causality keep them, for now, in the realm of thought experiments. They are useful there. They help us test where the edges of the possible might lie, even if they never solidify into metal and fuel. And then there is the quiet truth that we have never been entirely still. Long before anyone talked about starships, we were already riding one. The sun is our vessel, towing Earth and its neighbors along an orbit that takes around 230 million years to circle the galactic center. In the time since the first small creatures crawled onto land, we've completed only a couple of loops. Every life that has ever been lived has been part of that slow sweep, even though we've only recently learned to name it. So in one sense, the journey across the galaxy is already underway and has been for as long as Earth has existed. We are passengers on a vast, repeating route. We may never notice most of the scenery changing because it does so on scales far beyond one lifetime. But the motion is real. Every breath you take happens inside a solar system that is quietly arcing through space around a black hole you will never see. The hazards along that path, black holes, bursts of radiation, drifting clouds of gas, are part of what makes the Milky Way a real place, rather than an abstract figure. They would matter deeply to any future navigators. Courses would be plotted to skirt dense star clusters, to avoid the worst of the central maelstrom, to pass safely above or below the plane when needed. Gravity would be both a steering tool and a danger. Space would not be empty at all. It would be a weathered landscape, with calm regions and rough ones, with shoals and storms invisible, except in their effects on light. Light itself remains the constant thread. It is how we know black holes are there at all, how we map the arms, how we discovered that dark matter must be wrapping our galaxy in an unseen halo. It is how we build our star charts and how we measure our own orbit around the center. If anyone ever does try to cross the Milky Way, their instruments will be expanded versions of what we already use. Detectors tuned to many wavelengths, listening for pulsars, decoding spectra, watching tiny shifts in the positions of distant suns. Navigation at that scale is nothing more than an extension of what astronomy already is: careful attention to the messages photons carry. From where we stand now, at the edge of a small star system in a minor arm, full crossings are stories we tell rather than plans we draft. Our actual machines inch outward, a probe to Saturn, a lander on a comet, a pair of aging craft, Voyager 1 and 2, just beyond the sun's wind, feeling interstellar space with tired sensors. They will never reach another star, but they have already changed the meaning of out there for us. They are proof that we can send something of ourselves into the wider galaxy and hear it whisper back. Perhaps, someday, faster ships will follow them. Perhaps, tiny laser-pushed sails will skim to nearby stars within a human lifetime. Perhaps, automated factories will drift ahead of us, preparing distant systems long before any living crew sets out. Or perhaps our role will remain what it is now: to watch, to measure, to understand, to let light do the traveling while we stay anchored to this one turning world. None of these paths cancels the others. They are all ways of being in conversation with our galaxy. And that may be the gentlest answer to the original question, to ask, how long would it take to cross the Milky Way? Is on the surface to ask for a number, 100,000 years at light speed, hundreds of millions, with the kinds of craft we can build today. Something in between if we find new ways to move or learn to endure for longer. But underneath, the question is also about relationship. It is about how we fit inside a structure so large that its edges always lie beyond any journey we can actually take. We will probably never send a ship that leaves one physical rim of the disk and touches the other. We may never watch a complete crossing unfold. Yet every night, photons that have spent tens of thousands of years in flight finish their trip in our atmosphere, on our telescopes, in our eyes. Every day, our star carries us a little farther along its orbit, a tiny step in a circuit longer than all of written history. Every measurement we make of distant stars, every map we improve, is a way of reaching across the gap with understanding, if not with hulls and engines. So the galaxy stays both impossibly large and quietly familiar. Its crossing times remain beyond us, but its presence is woven into our ordinary days: the soft band of the Milky Way on a clear night, the tug of its mass on our sun, the faint signals we draw into graphs and images. We may never stride from one edge of it to the other, but we are already inside its journey, already sharing its motion, already lit by the same light that has been crossing it patiently for longer than any of our stories remember. When we say that the galaxy takes forever to cross, what we are really admitting is that our lives are short compared to the stage we stand on. The Milky Way is not being difficult on purpose. It simply exists on a scale that does not bend easily to human rhythm. That mismatch can feel discouraging at first, as if the universe were keeping something important always just out of reach. But if you sit with it for a while, the feeling begins to change. The impossibility of the crossing becomes an invitation to look, to listen, and to imagine, rather than to insist on arrival. Thought experiments about traveling across the galaxy are like long, slow stretches of a lullaby. They don't move our bodies, but they shift our sense of where and when we are. When you picture a photon taking 100,000 years to go from one galactic rim to the other, you start to feel how old the Milky Way is compared with us. When you imagine Voyager 1 needing more than 1 billion years for the same trip, you see how modest our engines still are. When you think about a generation ship drifting for millennia, or a near-light-speed vessel whose crew arrives centuries in their own time but tens of thousands of years in ours, you are really practicing a new kind of thinking, one that stretches far beyond a bedtime, a season, or a single human story. In that sense, the question, how long would it take to cross our galaxy, becomes less about building a timetable and more about learning to hold very large numbers gently. 100,000 years for light, hundreds of thousands or millions for fast ships, hundreds of millions or billions for the machines we can build today. These are not targets in a flight plan. They are reminders of where we stand on the ladder of scales, wedged between seconds and eons, between the ticking of a wristwatch and the slow turning of a spiral of stars. This change of perspective does something quiet but important. It softens the sharp line between reachable and unreachable. We may never cross the Milky Way with a physical ship, but we can cross it in understanding. Telescopes already do a kind of traveling for us. They gather light from the far side of the galaxy, from the central bulge, from the thin outskirts, and they bring those photons to a focus a few meters above the ground. In that focused patch of light, the whole disk is compressed into a pattern our minds can study. Data becomes a bridge where metal cannot. We also cross the galaxy in another way, through time. Every moment you are alive, Earth is moving with the Sun along its orbit around Sagittarius A*, the supermassive black hole at the center. We do not feel that motion. Our days are governed by the rising and setting of a much nearer light. But on the longer scales, we are always in transit. The spot in the Milky Way where the dinosaurs once watched the sky is not the spot where we are now. Millions of years from today, our descendants, if they exist, will look up at a somewhat different arrangement of stars from a somewhat different place along the same vast curve. When you realize this, the idea of crossing the galaxy starts to blur. There is no neat starting line or finish line, no single straight path from over there to over here. The Milky Way is more like a slowly turning city of stars, and we live in one of its drifting neighborhoods. To be born at all is to step onto one of its moving streets. The fact that we cannot walk from one side of the city to the other in a single lifetime does not mean we are separate from it. It means our relationship with it is ongoing and shared, rather than complete. From here, the forever of the galaxy becomes less a wall and more a backdrop. Our tasks shrink back into scale, understanding how stars live and die, how planets form, how black holes grow and merge, how dark matter shapes the rotation of the disk. None of these requires an actual crossing. They require patience, good instruments, and a willingness to work on questions whose answers may take more than one generation to unfold. In that way, science already behaves like a slow starship. Each generation of researchers passes on charts, tools, and stories. The next generation adjusts the course, refines the map, and adds new details. No single person arrives, but the shared picture grows clearer. There is a kind of comfort in that. When you listen to how long a galactic crossing would take, it becomes obvious that the universe does not measure success the way we often do. It does not ask us to finish the journey. It asks us to take part in it. To keep curiosity alive long enough that, over centuries, our species can move from guessing to knowing, from myths about spilled milk in the sky to precise measurements of spiral arms and central black holes. On that scale, every quiet night spent looking up, every hour spent tuning a radio telescope or processing data, is a small but real step across the map. The silence between stars plays a role here too, because the gaps are so large and the voices so few. Every signal we do find stands out. A supernova in a distant arm, a pulsar ticking steadily like a beacon, the faint glow of hydrogen gas tracing the skeleton of the disk. These are not just decorations. They are the signposts that allow us to chart the Milky Way from our single vantage point. Without the vast, calm sea of almost nothing between them, the signals would overlap and blur, and the map would be harder to read. Thinking about forever in terms of our own lives can feel heavy. A crossing that takes 100,000 years is easy to dismiss as irrelevant, something so far outside human experience that it might as well not exist. But another way to hold it is as a reminder that we are part of a story much larger than ourselves. Your life is not long enough to watch a star form, shine, and fade, but the atoms in your body were forged in such stars. You will not see the sun complete even a tiny fraction of its orbit around the galaxy, but you are being carried along that orbit every moment you exist. You will never feel a galactic year pass, but you are living in the afterglow of many that have already gone by. From this angle, the forever of crossing the Milky Way is less an obstacle and more a kind of gentle framing. It tells us that it is all right if our contributions are small and local. No one is expected to solve the entire puzzle. It is enough to add one piece, to measure one cluster more carefully, to discover one exoplanet, to refine one model of how the spiral arms form, to tell one clearer story that helps someone else feel at home under the band of light. Over time, those pieces accumulate into something none of us could have built alone. You can also feel this in the way the galaxy appears to change us without our noticing. Just knowing that it would take light 100,000 years to cross the disk, and that even our fastest probes are still only a few light hours from home, shifts the way everyday distances feel. A drive across a continent, which once might have seemed long, shrinks into an afternoon's errand when you set it beside the gap between our sun and the nearest star. A decade, which once felt huge, becomes a brief flicker against the span of even a modest star's life. This doesn't make our problems insignificant, but it does loosen their grip. It offers a quiet, cosmic perspective in which anxieties can soften at the edges. In the end, the answer to how long it would take to cross our galaxy is both simple and layered. Simple because the numbers follow from the speed of light and the size of the disk, at least 100,000 years for the fastest possible traveler, vastly longer for anything we are likely to build. Layered because those numbers carry with them questions about time, continuity, isolation, and meaning. They invite us to imagine black holes as waypoints, stellar deserts as long, quiet roads, and starlight as both illumination and instruction. And perhaps the gentlest way to hold all of this is to remember that, for our brief lifetimes, the Milky Way is not asking us to cross it. It is simply offering itself as a sky, a place to take measurements and to tell stories, to send small machines outward and to welcome photons inward, to wonder how long it would take to go from one side to the other, even if we never do. The galaxy is already wrapping us in its slow, turning arms. We are already on board. The rest, the crossings we imagine, the numbers we calculate, the futures we dream, are ways of getting to know our seat on this immense, quietly spinning ship of stars. On a still night, when the air is clear and city lights are far away, you can see a tiny fraction of that ship with your own eyes. The Milky Way arches overhead as a pale, uneven band. To the naked eye, it looks almost delicate, as if a soft brush of light had been drawn across the dark. Knowing what lies behind that softness, the distances, the timescales, the impossible crossings, does not make it harsher. If anything, it makes it kinder. It means that when you step outside for a moment and let your eyes adjust, you are doing the same small, human thing that people have done for tens of thousands of years, looking up at a mystery too large to solve and letting it keep you company anyway. You do not need to cross the galaxy to belong to it. You are already made of its dust. The iron in your blood, the calcium in your bones, the oxygen in your lungs were all cooked in stars that lived and died long before the sun was born. The time it would take to cross the Milky Way is written in a very quiet way into the atoms that make you up. They have been traveling, combining, and recombining across cosmic distances for longer than any map records. When you breathe, when you think, when you grow tired and drift towards sleep, you are completing a tiny loop in that much larger journey. So when the question of how long begins to spin in your mind, you can let the numbers settle, but you don't have to hold them tightly. It is enough to know that the galaxy is wide, that light is fast but not infinitely fast, that our machines are slow but getting better, and that our curiosity has already carried us much further than our bodies have gone. The rest can be a kind of quiet background music, a sense that above the ceiling, above the clouds, above the thin, bright layer of atmosphere, there is a great, slow story unfolding. And for a little while, you get to be awake inside it. When the size of the Milky Way leans over you and feels too big to hold, the mind almost reflexively reaches for a hidden door. If light itself needs 100,000 years to cross the disk, if our probes would drift for hundreds of millions or billions of years, it's only natural to wonder whether there might be some way to slide past all that distance. We've always done this as a species. Faced with a mountain, we look for a pass. Faced with an ocean, we search for currents, for trade winds, for a better hull. Faced with a galaxy, we start to imagine paths that don't move along the surface at all, but through the deeper fabric beneath. Wormholes are the picture that most often appears when people talk about such shortcuts. The idea is simple enough to draw. Take a sheet of paper, mark 2 dots far apart, then fold the paper so the dots touch. A straight line on the flat surface is long. A little tunnel through the fold is almost nothing. In general relativity, space-time is the paper. The equations do allow solutions where 2 distant regions are linked by a kind of tunnel, a wormhole with a throat in between. Step into one mouth, step out of the other, and the vast distance in ordinary space has been quietly sidestepped. On paper, That's all very clean. In reality, things get difficult almost immediately. Wormholes, as the equations describe them, are inherently unstable. They want to snap shut faster than light could cross their throats. To hold one open long enough for anything to pass through, you need something that behaves like negative energy, exotic matter that pushes rather than pulls, that bends space-time in the opposite direction from normal mass. We see tiny hints of such effects in quantum physics, but only in minuscule amounts and fleeting moments. Nothing like the smooth, controllable river of negative energy you'd need to prop open a tunnel across the galaxy. Warp drives sit nearby in the same family of dreams. Instead of punching a hole between 2 points, they imagine sculpting a moving bubble of space-time around a ship. Inside the bubble, the ship rests gently in normal space. Outside, space-time itself contracts in front and expands behind, carrying the bubble forward. To distant observers, that bubble could outrun a beam of light without the ship ever locally breaking the speed limit, because it's not the ship racing through space, it's space sliding around the ship. Miguel Alcubierre was the first to show that Einstein's equations permit such a configuration in principle. But again, the cost is steep. The amount of exotic energy required in the original design was greater than the mass of the observable universe converted entirely into fuel. Later refinements chipped that demand down, but even the most optimistic versions still call for energies and materials far beyond anything we can plausibly access. The road is there in the mathematics, but the toll booth is guarded by physics we barely understand. Other ideas drift in at the edges. Some theories suggest that our universe might have extra dimensions curled up too small for us to see. In some of those pictures, traveling around a long distance through a higher dimension could be shorter than moving straight through the 3 we know. Some models imagine cosmic strings narrow, incredibly dense filaments left over from the early universe capable of distorting space-time in unusual ways, perhaps offering strange gravitational shortcuts. Rotating black holes in certain idealized solutions hint at passages to other regions of space-time entirely. None of these possibilities have stepped out of theory into evidence. They live on chalkboards, in simulations, and in the gentle glow of science fiction. But they are not empty fantasies. Each time someone tries to write down a shortcut, they have to wrestle with the deepest rules of the universe. That wrestling teaches us things even when the shortcut itself crumbles. Thinking seriously about wormholes forces us to understand space-time geometry more precisely. Thinking about warp drives makes us probe the nature of energy and vacuum and the limits of what negative energy could really mean. Thinking about extra dimensions, cosmic strings, or exotic black holes pushes our understanding of gravity and quantum mechanics to their limits. In that way, shortcuts are not escapes from knowledge, but tools for making it. They are questions wearing adventurous costumes. Even if no wormhole ever opens its throat, the work done trying to understand whether it could has already given us clearer visions of how gravity behaves, how quantum fields fluctuate, how the early universe may have evolved. The dream pushes the science forward. There are gentler, more grounded kinds of shortcuts too, the sort that don't break any rules, but make clever use of the ones we already know. Gravitational slingshots are a good example. Voyager 1 and 2 gained much of their speed by falling toward Jupiter and Saturn and then whipping around them, stealing a little of their orbital momentum. The same physics governs the way galaxies bend the paths of light, acting as lenses that brighten and distort more distant objects behind them. Mass curves space-time, Curved space-time bends trajectories. Used wisely, that curvature can save fuel, time, or both. It's not hard to imagine a far future civilization learning to arrange such effects, like a network of ocean currents swinging ships past massive stars, compact objects, or even artificially sculpted masses to create gravitational highways that stitch parts of the galaxy together in more efficient ways. It's still not magic, still not instant, still bound by the speed of light, but it's a reminder that the universe already provides subtle tools for shaving corners off the long road. At the same time, the psychological weight of the numbers we've been carrying matters. When you hear spans like 1,000,000 years or 1,000,000,000 years attached to journeys, something in the mind recoils. Those durations are so far beyond anything a person can experience that they almost stop feeling like time at all. Shortcuts, whether they are mathematical tunnels or refined slingshot techniques, offer a kind of emotional relief. They whisper, maybe the wall isn't quite as solid as it looks. Even if we never find a real door through that wall, the whisper itself softens the feeling of being penned in. There's also something revealing in the way we keep coming back to these ideas. We recognize limits. We know the speed of light is an ultimate cap on motion through space. We know energy is finite, and the distances are enormous. And still, we lean against those walls just to see if they push back. That instinct says as much about us as it does about the galaxy. The Milky Way doesn't just exist as a collection of stars and gas. It exists as a kind of mirror for our curiosity, big enough and remote enough that our imagination has to stretch to even begin to meet it. After wandering through all of these possibilities, wormholes that may never stabilize, warp bubbles that may never form, clever gravitational tricks that may only ever trim, not erase. The long haul, it feels right to come back to the one place we truly know. Every calculation and every dream, every contour of the map we've drawn, starts from a particular point, a small planet circling a modest yellow star, tucked into a quiet spur of a spiral arm. Our sun lives about 27,000 light-years from the galactic center, in a region that's neither crowded nor empty. We're not in the blinding bustle of the core, where stars jostle close and supernovae are more common. We're not in the sparse outskirts, where heavy elements are rare and new stars are fewer. We sit in a kind of middle ground, often called a galactic habitable zone, not in a technical, guaranteed sense, but in the softer sense that conditions here turned out to be gentle enough for planets to form, oceans to settle, chemistry to experiment, and life to persist for billions of years. When you stand outside on a dark night and see the Milky Way as a hazy band, you're looking along the plane of the disk from inside it. The brighter, denser patch toward Sagittarius marks your gaze inward through more and more stars, dust, and gas. The slightly thinner stretch toward Orion and Perseus marks your gaze outward, toward the quieter edges. In every direction, interstellar dust blocks some of the view, turning parts of the band ragged and patchy. Yet from those ragged hints, plus all the invisible wavelengths we can't see with our eyes, we've managed to reconstruct the grand shape, a barred spiral, arms curling, disk warping, halo extending. And we've done all of that without leaving home. That might be the most quietly astonishing part of the story. We have not crossed the galaxy physically. We have barely stepped beyond the solar system. Yet from this one orbit, on this one world, we have measured distances to stars, mapped the spiral arms, weighed the dark matter halo, pinned down the mass of the black hole at the center, and traced streams of stars from past mergers with smaller galaxies. Every bit of that knowledge came from light and other signals that happened to pass through this tiny neighborhood and fall on instruments we set up here. In that sense, we are already travelers, but travelers of understanding rather than of metal and fuel. We have sent our questions outward and let photons, radio waves, and particles bring the answers back. That journey is not constrained by our short lifespans in quite the same way. A project can last decades. A catalog can be handed from one generation of astronomers to the next. A mission launched by one group of engineers can still be returning data to their grandchildren. The crossing of the galaxy in knowledge is a relay, not a sprint. Seen from that angle, the forever that haunts physical crossings becomes less of a barrier and more of a background condition. The galaxy is large. We are small. That's not a failure. It's just the setting. Within that setting, what matters is how far we can extend our awareness from this one small sphere. Landing a robot on a comet is a step. Imaging the event horizon of a black hole is a step. Detecting planets around other stars, listening for faint whispers of neutral hydrogen in distant arms, timing pulsars until their ticks reveal ripples in space-time. Each is another small stride in the same direction. And all of it begins with home feeling steady under our feet. The more we learn about the hazards that lurk in the galaxy, black holes, stellar explosions, intense radiation, the more this steadiness stands out. Earth is not perfectly safe. It has its storms and quakes and long histories of impact and extinction. But compared with much of the cosmos, it is astonishingly gentle. Our atmosphere filters lethal rays. Our magnetic field deflects charged particles. The sun's output is stable on human timescales. Our orbit is nearly circular and comfortably distant from our star. In the grand, unruly structure of the Milky Way, we've ended up in a tiny pocket where water can stay liquid, chemistry can remain slow and subtle, and life has time to grow complex enough to ask questions about all the rest. So, when we talk about crossing the galaxy and the numbers start to tower over us, it can help to return to a simpler thought. Before we go anywhere, we are already somewhere. Our coordinates are not just a line in a textbook. They are a location in a real, evolving structure, a spiral of stars, gas, dust, and dark matter that has been turning for billions of years and will keep turning long after we are gone. To know where we are inside that spiral is already a profound form of belonging. It also changes the feeling of insignificance that can creep in when you hear about 100,000-year journeys. Yes, our ships are slow and our lives are short. Yes, we will not personally ride a vessel from one galactic rim to the other. But from this small planet, with our small tools, we have already done something extraordinary. We have looked up at a faint band of light and learned that it is a cross-section of our home galaxy. We have taken what was once a mythic river of milk in the sky and turned it into a map with distances, velocities, and histories attached. Every time we refine that map, every time a new telescope comes online or a new survey publishes its results, the Milky Way becomes less of a vague glow and more of a place. Not a place we can walk across, but a place we can describe, visualize, and feel part of. The crossing, in the strict physical sense, may well remain a dream measured in forevers. The understanding does not. It grows a little more complete with every quiet observation. And in the end, on nights like this, when the world around you is dim and the sky is Perhaps just a little visible through a window or a crack in the curtains. That may be enough. You do not need to hold the full span of 100,000 years in your mind. You do not need to solve the problem of wormholes or warp drives or exotic matter. You can let those ideas drift like distant ships on a distant sea, interesting but far away. What you can keep close is simpler, the knowledge that above you there is a galaxy, that you live inside it, and that your thoughts are part of how it comes to know itself. You can let that thought be a kind of blanket, a reminder that you are small, yes, but also woven from the same elements as stars. Brief, yes, but bright, in your own narrow band of time. If these wanderings through distance and time have brought you a little calm, a little soft wonder, you're welcome to leave a quiet like or subscribe so you can find your way back the next time we drift out among the stars together. There's no rush and nothing you need to remember. You can let the numbers and images fade the way starlight fades when clouds roll in. They'll still be here, waiting patiently whenever you feel like visiting again. For now, it's enough to be where you are, to rest under the familiar weight of your own sky, with the Milky Way arched invisibly above, turning slowly, steadily, far beyond the pace of any worry. Let that slow turning hold you for a while. Let your thoughts quiet, like dust settling in a sunbeam. The galaxy can look after its own crossings. Tonight, your only journey is from waking into sleep. Sleep well, and good night.